Good morning or good afternoon, depending on your time zone. I'd like to welcome everyone to the Fibre Channel Industry Association's Protocol Analysis for High-Speed Fibre Channel Fabrics in the Data Center. My name is Joe Kimpler, and I'll be your moderator today. Today we have an all-star cast of presenters from Teledyne LaCroix. We have David, who is a member of the FCIA Board of Directors and a Senior Product Marketing Manager. We have Yamini Shastri, a Senior Engineer from Viavi Solutions, and she will also be presenting. And myself, Joe Kimpler, is the moderator, and I'm from Addo Technologies. I'm the Global Manager of Alliances Enablement. Today, as the moderator, I'll be taking questions during the presentation, and we'll be interjecting them as soon as possible after I receive them. However, if we don't have a chance to ask David or Yamini your question during the presentation, I'll be sure to ask them after each presentation. We also have time for Q&A at the end of the presentations. And just to note, a PDF of the slides will be posted to the FCI website for reference material that you can share with your colleagues. A little bit about the FCIA. The Fibre Channel Industry Association is made up of a who's who in the fibre channel industry, with marquee companies like Amphenol, Addo, Brocade, Cavium, Marvell, Cisco, DCS, Hewlett-Packard Enterprise, Sandblaze, TE Connectivity, Teledyne LaCroix, and Viavi. The FCI member companies are devoted to the fibre channel, which is a dominant fabric in today's data centers. Fibre channel is deployed in about 90% of the Fortune 1000 data centers in the world, and comprises approximately 90% of the server connections to all flash storage arrays. Fibre channel has a unique advantage over other networking technologies in terms of its rock-solid reliability, unmatched performance, and massive scalability. A little bit more about the FCIA. The FCIA promotes the advancement of the fibre channel technologies through emerging standard committees like the T11. We maintain resources and support activities to ensure multi-vendor interoperability for both hardware, interconnect, and protocol solutions. The FCI activities include promotion and marketing of FC solutions, educational awareness, hosting public interoperability demonstrations, and fostering technology and standards conformance. Today's agenda will be the basic premise of testing, line rate analysis, protocol of the PHY, performance metrics, an example of how to debug, and traffic impairment. With that, I'd like to turn it over to Teledyne LaCroix's David Rogers, the Senior Product Marketing Manager for Teledyne LaCroix. Dave?
Thanks, Joe. Good morning and good afternoon, good evening, everyone on the line. As Joe's pointed out, we're talking about the use of protocol analysis in the data center. And most people would think of protocol analysis possibly from a standpoint of we only need it to be in the, we only need it when we're doing development and debug and initial testing. But what we've determined based on the principles of test is that the faster we go, the more problems we have and the more essential it is for data center managers or everyone in the ecosystem to be aware of protocol across the board. So in previous presentations from the FCIA, you've heard about slow drain, and you've heard about interoperability. All of these things are examined and tested through the use of test and measurement tools, not the least of which are protocol analysis, protocol-specific analysis tools. And as evidenced on the screen, our basic premise statement is that the faster we go, the more speeds and the port count densities. We have more challenges into meeting the demands of our users and to be able to interoperate across all of the different participants in the fibre channel ecosystem. And moving on to our test and measurement considerations across the board, whether or not we're in the development community or whether in the support community, the who, what, when, where, why, how much, how many of test and development is in front of you. The considerations are in front of you here. What is it we're trying to figure out? What are we trying to understand and correct? When and where does it manifest? Can I reproduce these issues either in a lab setting or live? Can a root cause be determined definitively? What kind of fixes can we put in place? How do we put curative measures in line? And then how do I test the remedy and make sure that it's the right fix? So those are some of the things that we're bringing to you today. In the case of expectations, we have our considerations. What do we expect out of this? Through the development community, we expect vendor interoperability. We want to see that when we buy product from whoever, it plugs in and it works. Of course, now we're the mission critical applications that we have demand reliability and inconsistency, and where we saw minor imperfections in certain aspects of fiber channel in the past, now those aren't acceptable because they provide latencies and they provide problems for the users in the applications. We also expect that the legacy product that we have deployed will work well with the new products that we're bringing in to get ready for the next speed bump in our data center. Of course, the growth in the content delivery doesn't change the fact that we still expect 5 nines of uptime in these storage fabrics. And from a standpoint of understanding what's going on in the environment, knowing what's on the wire, which we'll talk to here in a little bit, is essential because we have so many things interoperating and protocols at the various levels. We can't really determine what's happening without a clear vision of what's going on in these fabrics. In the case of test and measurement today, the signal integrity and the hardware engineering teams are using BERTs and PERTs and scopes and traffic generators to try and just get the electrical roadway paved. And of course, as you might see, we're going from NRZ signaling to PAM4 signaling. So we don't envision that it's going to get any easier to do these test and measurement situations and setups. But what we do see in the existing tools is a limitation to determine what's actually happening at the PHY layer. And by that I mean there's a protocol inherent in the basic physical structure of the fiber channel environment as well as the upper level applications. So certain questions that we might want to answer that are problematic are why didn't our links come up as we thought they would? Or in the case of speed negotiation, both participants are advertising their 32 gig capabilities, but for some reason will only link up at 16. And then once that speed negotiation completes, transmitter training seems to have a problem, and we're failing that, so we fall back into a loop of trying just to get the fabric up. And then with the use of some of these older tools like the scope, how do I determine the link transactions and what's actually being sent simply by looking at the waveform patterns on the scope? Yes, you can roll out a logic analyzer, but that seems to be a tool of last resort. But where we're seeing some of the advancements and some of the things that Yamini and I will be speaking to today are an update in the tool catalog for the testing of the PHY in and of itself. We also see some high-speed sampling scopes going up to 100 gigahertz. That's important for setting the stage for some of the next things you may or may not be doing. I don't envision those in a data center particularly, but as far as the ecosystem of test and measurement for successful fiber channel deployment, it's going to be an important additional tool. What we are seeing is specialized enhancements in traffic generation and analysis tools. So being able to decode the sublayers, being able to actually look at the transactions of packets at speed negotiation, transmitter training, base layer communications. Those are being brought into your generators and into your protocol analyzers. Then we talk about specifically line rate analysis capabilities, what we call pass-through tapping, and then capturing at the bit level to be able to decode the specific bit points. And then what does traffic impairment or jamming help? How does that help us in the test and measurement? Going back to how do I test my fix? And then, lastly, the road is becoming smart or smarter. Not unlike having an electric car that's going to drive across a intelligent roadway, the roadway of fiber channel is becoming more intelligent and providing information to the carriers, the frames, and the passengers, the data blocks within those frames. So I think right here I passed it over to you, don't I, Yamini, at the talking about the tools here?
Sure, yeah.
Outstanding. So with that, Yamini?
Hello, everyone. My name is Yamini. I am from VRV Solutions, And as David mentioned, there are many advancements in test and measurement market, and here we are trying to list a few of the tools that are available to us to debug and troubleshoot performance issues in fiber channel networks. These tools can be categorized into monitoring tools, inline analysis tools, or generator and jammer tools. And we'll talk through these in detail in the next few slides. Here the column headers are referring to the tools, and the row headers are referring to the application areas or test areas where these tools can be referred to, can be applied to. So the first two columns here, we're talking about testing capabilities built into the SAN components itself, like the fabric monitoring tools and the end device metrics available on the ASICs in these SAN components. And these provide a very high visibility and advanced metrics and counters built into these ASICs. There are thousands of counters built into these ASICs that are then integrated into advanced software tools to monitor traffic in these extremely high performance, high reliability SANs. Then we have the analyzer tools, which are the hardware analyzer tools that can sit in line and capture traffic and trigger unknown error situations. Also, they provide a pretty extensive post-capture analysis capability that can be extremely resourceful in pinpointing the problem components in the SAN or problem areas. And these the capability is across various protocol layers in the fiber channel stack. And we also have the deep packet inspection tools, which are the software analyzers, and they could be used to look at the bit and bytes on the wire, bringing it all the way down from the end device monitoring to a wire level analysis. Then you have the scopes that David talked about for testing signals at a PHY layer. And then we'll talk about the generator and I/O tools and jammer tools in the next few slides here. So what can the generator tools do? Here is a diagram of a very simplified link in a switched environment. You have your server connected to a storage system through a switch. And of course, we can place analyzers on any of these links, both pre and post deployment to look at any issues that might come up. And in a typical SAN, the server has multiple applications running over many virtual machines, and all are connected through one or two physical HBAs, right? And the performance problems are usually reported by these application users, and the storage admin then has to gather logs and tool dumps and monitoring tool reports and any traces collected and works through them to analyze the issue. But if it's a mission-critical application, the admin may have to do more of a trial and error where they remove other less critical applications or stop some backup services or temporarily even remove certain links and devices that could be potentially the bottleneck cause for the slowdown. And otherwise, if it's not a mission-critical application, it's possible to bring all this information back to the lab and test it in the lab. And in a test setup, we could actually simulate the entire server-side setup using these advanced generator and I/O tools, which could create application-specific loads to simulate various real-world applications. The generation and I/O tools can be used for performance testing by stress testing the various parts of the link, or they can be used for compliance testing and functionality testing by generating various implement-specific functionalities. And most importantly, they can also be used for data integrity testing, where there's a bit level comparison, write, read, compare sort of capability in these I/O tools. And the analyzers can, of course, be used for capturing analysis and triggering on protocol violations, errors, and can be used in interop testing. Further, we have the jammers, which are typically used for error injection and create bad device behaviors and then test DOTs on how they recover when under such error situations. And towards the end of this presentation, we'll go into the details of various error scenarios that can be created using the jammers. So here we'll talk about a little bit about specialized generator tools that are meant for load testing SAN links. A SAN enabled for high performance storage connectivity should transfer data at full potential of the available bandwidth on each link of the topology. And the load testers platforms are used to create bandwidth throttle by sending wire speed traffic and testing for sustained throughput while monitoring latency and dropped frames and error situations under these various load conditions. And of course, in a different combination of these tools is used for overall testing and analysis, both in pre- and post-deployed storage networks. Okay, so let's switch gears a little bit here, and then we will talk about how we'll apply these tools at various levels or various layers in a fiber channel protocol stack. And then we'll look at what metrics and features do we actually focus on at each of these layers. This slide right here is printed from the Fibre Channel Interoperability Webcast, and it shows the mapping of the Fibre Channel protocol stack onto the traditional OSI stack. It also lists how the FCoE protocol stack is mapped on both the OSI and the Fibre Channel stack. So FCoE is typically Fibre Channel over Ethernet, and you would see the upper layer protocols using the Fibre Channel, whereas the PHY and link layer using the Ethernet, and there is a mapping using the FCoE mapping layer at the network layer. On the typical Fibre Channel stack, many of you are very well aware of what the functionality of each of these layers is, but for those who don't, we're going to quickly talk through these. The FC0 defines the PHY, including the cables, the transceivers, receivers, and the physical media and the speed of the connection. FC1 is the transmission protocol and talks about the encoding, decoding of signals. And FC2 is the network layer that defines a lower layer Fibre Channel protocol, such as the flow control protocol, and the class of service and framing and signaling protocols are defined at this layer. FC3 is a common services layer. It's a thin layer that could eventually implement functions like encryption and advanced algorithms, but for this presentation, we're going to focus on link services that is defined at this layer. FC4 is a protocol mapping of the upper layer protocols onto the Fibre Channel stack. For example, FCP SCSI defines the mapping of SCSI protocol over Fibre Channel, and FC-NVMe defines the NVMe mapping onto the Fibre Channel protocol layers. So this is just a repeat of the same, but here we're going to focus on what issues should we be focusing on at each of these layers. FC0, as we mentioned, defines the PHY layer. So we'll be looking at the cabling issues, the transmit-receive issues, basically making sure that we have a clean PHY layer to begin with when we set up the SAN, right? FC1 is the transmission protocol, and it defines the encoding, decoding of signals. In this, we'll be looking at any transmission protocol errors, such as PSEs, sequence errors, or loss of sync errors. And we'll also be looking at speed negotiation and transmitter training issues that David mentioned a little bit in his introduction. And then FC2 will be talking about framing errors. This layer defines the framing and signaling protocol and a very important flow control protocol that is crucial for Fibre Channel networks to operate smoothly. And here we'll be looking at any of the flow control issues like the buffer-to-buffer credit issues. FC3 would be the link services, and here we want to make sure that all nodes in the network are properly configured and expected functionality is advertised as expected, right? The expected functionality on each of these ports is advertised. Like during login, the buffer-to-buffer credits available are advertised, the number of concurrent sequences supported, and the class of service and data field size and things like that are advertised at this layer, and we want to make sure that these are advertised as expected by each port. And finally, when we look at the FC4, the protocol mapping of upper layers, we'd be looking at latencies and protocol violations and exchange timings and such. And we'll go, for the rest of the presentation, we'll be talking in detail through each of these layers, starting with FC0. And here I'm going to hand it back to David to talk through these layers.
Thanks, Yamini. So we've kind of lumped FC0 and FC1 into for the purposes of expediency in this presentation, into one category. In the case of physical media, there's really not much that we're going to see with a protocol or a scope or any other tool, other than the fact that we either have light on the fiber or we have an electrical connection through the cabling. We can often determine through the use of specialized tools whether or not the cable is supported by the switch. In the case of a specific lockout, or a vendor decides that they're only going to support certain features or functions of specific cables or optics, they'll put in logic to make it work. That's typically done by a specialized I2C analyzer to read the information coming out of an EEPROM in a cable. When we get into transmission and protocol and data link layer, the FC1, this is where we start to see the real application of a protocol tool paying off. As evidenced before by one of the slides that I had with the graphic of our eye diagrams, it's great that the scope gives us a picture of what our eye diagram looks like. But again, it doesn't do anything for helping break down what's actually occurring in the way of the transaction at these FC0 and FC1 layers. So obviously the things we're looking for and adapting in a quote-unquote protocol sense is speed negotiation. What are the two? What is the link under test communicating back and forth as far as speed requirements? Do I have mismatched optics? Do I have a cable that's not supported, or some other variant that's causing a problem? And then, of course, as we get faster with the speeds, transmitter training is becoming that much more important to be able to ensure we have a good communication over the long period of time. And in fact, that continues on a periodic basis depending upon the nature of the link. And then lastly, forward error correction. FEC is becoming more and more popular in order to maintain the 10 to the minus 15 error that we're striving for in fiber channel. It's all very important that we look at these things at the lower level, and I have a couple of slides that show some of the data points and bits that we're looking at in there. Remember that no two physical implementations by vendors are the same. We all read the spec, we all look at how to implement that, and then we go into the lab and we build something. But invariably, we're going to have a nuance or a difference in how we view those things, especially at the physical layer. So again, having the ability to look into that from a neutral third party and be able to see what's going on the links is where we're looking at the application of protocol tools. The goal, of course, is T11 specification and compliance. You have to be transmitting in compliance with the specification in order for the rest of the ecosystem to accept you and be able to see you in its environment. And the last point that we drive home in every presentation, and especially the one we had with Barry and Tim from UNH, was interoperability. We test to make certain that not only are the new products working well with each other, say at 32 gig or the upcoming 64 gig specifications, but will those new products also support the 4, 8, and 16-bit speeds that we have from our legacy applications? In the FC1 layer, and this is where we get into some of the things that we can actually see. If you can't read some of the bit values on the screen during the presentation, when you download it, please, you can dig in. But you can see by the representation that there's a variety of variables in a transaction here at the link layer that could go awry. Frame delimiters, start of frame, end of frame. Just our primitive signaling, between 8 and 16, we went from single primitive to back-to-back primitives. Am I still complying with the framing and signaling that I need to at FC1? And then, of course, some of the other primitive sequences, link ready and reset, NOS, where we're seeing the encoding and decoding and transmitter training. These are all important values in here. And as you can, like I said, if you can't see it on the screen right now, when you download the application or download the presentation, you'll see all the different bit values that could be awry and otherwise causing a problem that you wouldn't see necessarily using a scope. And then doing the characterization of your transactions, being able to put markers in there and see if I'm actually complying with that. This is important in the data center. So this is important in development, of course, but it's important in the data center. If you have the IT position to keep everything up and running. Your 5 nines are important, and you actually want to get into characterization of what's going on before you bring in your third-party service or your OEM vendors for getting remediation. With that, I'm going to pass it back over to Yamini. She's going to talk to us about the FC2 layer.
Yeah, thank you. So, all right, so assuming we have a clean file layer and no errors on the link, we move on to the FC2 layer where the class of service, framing and signaling, and flow control is defined. We're assuming there are no framing errors and the appropriate class of service is asserted, the first thing we want to look at this layer is the flow control protocol. Flow control protocol is typically what makes fiber channel lossless. It's a mechanism that's built into the protocol so that a source port can make sure that there is enough buffer space at the destination port to receive frames. It does this by keeping count of credits available to send frames, and the destination port grants credits to the source port before a frame can be sent. This way, it always ensures that there is enough buffer space available on the destination port to receive the frame. And each credit allows the source port to transmit one frame, and when the frame is received at the destination port in process, the destination port replenishes the credits. The maximum number of frames that can be transmitted from the source port is specified during the Fabric login by an endpoint, and both sides advertise it, and both sides maintain a credit count going forward, adding a credit when an RRD is received, a transmit credit available when an RRD is received, and subtracting a credit when a frame is transmitted. It's very simply put, it's keeping a balance of credit versus frame counts, and stopping frame transmission when a credit count ends up being zero. The balance ends up being zero, and this is called out of credit situation. So when devices replenish credits in time properly, as mentioned by the protocol, everything works smoothly. But say a device does not return buffer credits fast enough, this would cause the other side to stall sending frames, and if this happens on an end device, it can actually stall the transmit side of the switch, causing frames to back up through the switch and causing fabric congestion throughout the entire send to the other end device that's actually the source of these frames. So let's look at a quick example. In this figure here, the host port is connected to a switch A, which is connected to switch B, and then to two targets, A and B, target A and target B. Say the targets are sending traffic to the host port, and we notice a performance issue in this direction. We first want to look at the flow control protocol, right? So if the host port for some reason does not send credits fast enough, it will cause the switch port on A connected to the host port to run out of transmit credits eventually. After it doesn't replenish the credits, eventually the switch A port connected to the host will run out of credits and will stop sending frames. But switch B will still be routing the frames from the target towards switch A, and when the switch A buffers enough number of frames to its limit of credits, buffer credits available, it will stop sending those credits out to replenish the credit space on switch B, which will stall frame transmission from switch B. And the same thing will continue through the switches until the end points where the links connected to the switch B to targets will also be stalled for any frames, because switch B will then run out of its received credits and stall the frame transmission from target A and target B. So this situation is called a slow draining. This situation is called a slow drain, and in this example, the host is the slow draining device, and these can cause severe performance issues in a SAN. There could be two reasons for slow drain. One is a bad device behavior, and the other is lost credits. If a credit is lost, then the frames sent won't be replenished. And if too many of these occur, then there could be, the source port could be out of credits. But lost credits are usually not permanent, because lost credits are caused by corrupted primitives, and that would show up as other sort of issues on the physical link as well. Typically, if a credit is lost, then it's usually recovered using credit recovery mechanisms. But when a device is behaving badly or too slow in returning credits, that's when we usually hit these low drain situations. There's an excellent webcast on FCIA. It's an FCIA webcast by Earl Epplenis and Ed Mazurek, describing in detail this flow control protocol and how to monitor for a slow drain device and what the effects of a slow drain device would be. If you're interested, you should watch that webcast to understand more about this. So say we figure that there is a slow drain device. What metrics should we look at when detecting the device, right? First and foremost, you want to look at zero transmit credit situations. How many times is a port in zero transmit credit situations, and follow the direction of the TX credit, the transmit credit counters, to find the slow drain device. And that's very important to make sure that the direction is the direction of the transmit credit out of credit situation. And in high throughput environments, usually zero transmit credits could be very common because the frames are being sent out so efficiently that it can end up being in zero transmit credit situation. So it's very important to look at this zero transmit credit count in respect to the frame count. You want this ratio to be pretty low, and if the monitoring tool allows for setting triggers on this, that's a very critical metric to look at, which is the zero transmit credit counts versus the frame count per direction. The other metric that also points towards the same thing is the time in zero credit situations. Again, these counters should be pretty low, and in association with the time in zero credit situations, you also want to monitor for dropped frames. So on a port, the time in zero credit situations is extremely high, and then you see discarded frames on that port. That typically points to a slow drain situation or out of credit situation on that port, which means that that port is spending a lot of time trying to receive a credit and trying to send out the frames that are in its buffers, but at some point it times out and it starts dropping the frames. The last metric that I'm going to talk about here is the frame to R-ready times. On a given buffer to buffer link, the frame to R-ready times should typically be steady. Huge changes in frame to R-ready times aren't expected. And again, setting these thresholds, if the tools allow for it, can aid in figuring out the problem device. The effect of these slow drain devices or out of credit situations could be simple performance dips, or when, as I said, when there are discarded frames, this can lead to link timeouts and application failures as well. So here I'm going to talk about a simple debug example. Basically, the idea here is to point out the effect of delayed credits on megabytes per second or throughput on a link. In the first graph here, that's the red graph shows a dip in the throughput by about 50% on a link. So the first thing, after making sure that there are no errors on the link or all the things that David mentioned about transmitter training and speed negotiation, everything is as expected, you want to look at, on the same link, the megabytes per second in the other direction, which is on the second graph here, which is the yellow graph, the yellow line drawn. That actually shows the megabytes per second in one direction had a severe drop, but the megabytes per second in the other direction is still okay, steady. So then the next thing we'd do is to plot the frames to R-ready time in the direction of the throughput dip, right? And here we see that the frame to R-ready time, which is in sort of a light blue graph there, shows that the frame to R-ready time increased on this link for some reason on that direction, which means that the credits are being replenished slower than usual before the throughput dip. So this performance dip is, and it's at the same instance that the performance dipped on that link. So right here it shows you that the performance dip was because of a credit delay and a delay in replenishing or sending the R-readies back from the receiving port. All right, moving on to Fibre Channel 3 layers. David, you can take it up.
Thanks, Yamini. To reiterate Yamini's point there just for a second, these are conditions that you can't see without having some sort of third-party tool that is designed to sit in your fabric and give you a clear view of both sides of the environment. To that point, we'll move into what we're talking about with Common Service Layer FC3. I don't want to say one layer is more important than the other layer because they all have to work uniformly, but I believe that FC3 is the dispatcher for your communications. And the three basic, or the three main categories that we want to examine and understand what's going on are link services, link controls, and then the extended link services. With respect to the basic link services, and this is just a very brief subset of those, but they're common: abort sequence, non-op, BA accept, and BA reject. With respect to what these do in the environment, the roadway is now paved. We know how many cars and how fast those cars can go on the roadway in FC1 and FC2. Now we're actually getting to, what am I doing with the street lights? How do I get these cars back and forth and let people know things are happening? So in the FC3 and the link services, why is this important to the data center manager? Well, a lot of the things that we're talking about here are going to be showing up in the fabrics and in the layers here when you can look into them. So how do I know that I have abort sequences? All I know is that the link dropped. But to the point of the slide and what the graphic shows here, you look at all the different bit values that are possible in just a simple BA accept. There's a variety of different things that could go awry, whether it's a sequence, whether it's an OXID or an RXID, or any of the other minutiae values in there. These are things that can cause the problems. Remember, we talked about earlier the fact that minor imperfections, once acceptable, now are really deleterious. And this is where you can see the minutiae of detail that may be important to understand to go, I now have a problem, I have a resolution to the problem. In the basic link controls, of course, we have, I'm busy, I can accept it, I can reject it, I acknowledge that you're sending me things. Again, the minutiae of certain aspects of these transactions is very important to understand, not only from a development standpoint, but from the diagnosis in the real world of your fiber channel fabric, what's going on. So we have a lot of different values in here. The extended link services, not that anyone's better or worse than the other, but this is where we get into the really heavy-duty stuff with your logins, your port logins and your fabric logins, your accepts and your rejects. Again, if I'm logging in and I'm setting incorrect values, or if I've got some problems with the bit values of what I've sent in that packet, in that frame to get a login, I'm not going to do it. It's not going to happen. And your ASIC, your fabric management, or your vendor diagnostic utilities will report saying, I sent the port login, and the other side is going to say it didn't receive one, so you don't really know where to point the finger to figure out what's going on. Again, dropping in a third-party tool where you've got the opportunity to see both ends and say, I see what's happening here. I can actually drill down in and provide a value to say, hey, I'm seeing a problem with a controller chip. It's reporting back something incorrectly, and here's the manifestation of that error in the extended link services. Yamini, back to you.
Awesome. So here we're back to the top of the protocol stack, and the Fibre Channel 4 layer is the protocol mapping of the upper layer protocols onto the Fibre Channel stack. So here we'll talk about more of the protocol latencies or exchange latencies, and see what sort of metrics we'd be using to look at the upper protocol layer latencies, right? So here, okay. So the three metrics that are commonly used for performance measurements are the throughput, latency, and IOPS. The throughput is typically defined as the rate at which bytes can be transferred in and out of a system. The IOPS are the number of operations a device can handle per second, and the latency is the overall time it takes for a read or write operation to complete. And these metrics are somewhat related, where the throughput is IOPS times the IO size. So as the IO size goes up, you'd expect the throughput to go up and the IOPS to come down. So when benchmarking these metrics, it's really important to state the IO size, the read-write patterns we use in the traffic, and the connection speed, basically the bandwidth available. And in addition, QDIP supported by both the host and the target, and of course, what's the maximum QDIP supported by the protocol, that's a very important metric, because on a controller side, the controller has its own limit of how many pending IOs it can support. And pending IOs are a number of concurrent exchanges that can be on the wire waiting to be completed. And the controller can have its own limit across all the hosts it's connected to, and the host HBAs can have its limit across all the controllers that it's connected to. So these metrics are very important for any upper layer protocol measurement. So let's quickly look through how the FC4 mapping is done. So for example, SCSI is transported for the FCP SCSI transported over fiber channel, or FC-NVMe, where NVMe is transported over fiber channel. There is fiber channel creates a one-to-one exchange mapping. By that I mean the one SCSI exchange is mapped onto one fiber channel exchange. And here in this diagram, we see a bunch of user terminals connected to a fiber channel SAN, and through whatever network is connected through from the user to the fiber channel SAN, say user 2 requests a document from the storage. That request may be routed through server 1 there, which is on the extreme left. And server 1, the HBA on server 1, then splits this request from the user into multiple fiber channel exchanges, depending on the configurations of the fiber channel HBA there, right? And it sends these commands to, say, storage 3. It sends a bunch of commands to storage 3, and storage 3 then sends the SCSI data frames back to server 1, and the status associated with each of these exchanges back to the server 1. And once server 1 gets all these good status is back, it accumulates the payload contents and sends the document to user 2. So here we're looking at the mapping of an upper layer onto the fiber channel exchange, and how the fiber channel HBA can split an application request into multiple fiber channel exchanges, right? So the same thing, when we talk about latencies, the application request to response time is the application latency that we're looking at, which then passes through the HBA, and the HBA can split the given request, the given IO request from a user into multiple fiber channel exchanges here. In each of these exchanges, for a fiber channel exchange, the protocol defines multiple phases: the command phase, the data phase, and the response phase. And the data phase typically could be one or multiple sequence bursts. And each sequence is sent as a bunch of frames. So typically these frames, sequences, data phases, and exchanges together constitute an application request. Of course, for the application request to be successful, all these exchanges have to be completed in a given time and have to be completed successfully. So when we're talking about application latency, that could be different than what we look at on wire with these exchanges. And say one of these exchanges fails, then the application latency could be increased, because then it has to be retransmitted by first the host has to discover it, retransmit it, and then that adds up to the application latency. So it's really important to look at the exchange ages when we are seeing some sort of application latencies. So here is a read exchange where the host sends a command to the target. The target can send back one or many data sequences and, of course, follows it up with a status. In this case, the exchange age is defined as the command to status time, and the exchange age is further split up into command to first data time, and last data to status time. If you look at the command to first data time here, we're talking about a full round trip from the host to the target and target back to the host with the first data frame. So this typically gives us, depending on where we measure this metric, it's typically the time it takes for the target to respond back with the first data frame. So this is called first response time from the target on a read command. If I I'm going to go forward actually onto the next slide to look at a write command exchange. In a write command, the host sends a command, the target comes back with the transfer ready, and then the host sends all the data in, again, one or many bursts. In this case, the command to first data time actually has 2 round trip times, right? The command going to the target sending back a transfer ready, and then the host responding to the transfer ready with the data available. Typically, the first response time is the command to transfer ready in this case, because that's showing the first round trip time of an exchange. And because the writes, typically the host has the data available, it sends out all the data right away. So we want to see steady times for these metrics when SAN is up and running, and on a link when the host and target are consistently talking and there is pending requests on the link. In cases where these show extreme changes, we can use these metrics to point a target inefficiency or a host inefficiency. And in addition to this, performance hugely depends on support for pending IOs and higher queue depths on both host and target, as we mentioned. On a high-performance system, we expect to see steady queue depth, right, and steady exchange age timings. Large deviations in these values usually point to inefficiencies. So, for example, when application requests are pending, you always expect to see maximum pending IOs on the link. The host should keep issuing commands to the maximum queue depth supported by each side. When the host issues a command, it keeps the context information in memory, right? All this, the number of pending commands and the context information per command, and the IO context has to be available when the data comes back from the target to send the data to the associated application. So higher data rates place a huge burden on hosts on the HBAs for faster context switching, and the HBAs typically do all of these in the hardware buffers. So we don't expect huge delays on the host side when there is enough stress on the link where the host has to keep enough pending IOs on the link. On the target side, there could be inefficiencies too, right? And that could throttle throughput. For example, write cache is typically used for faster write latencies on the target. And when many virtualized applications send large number of requests, it can overload the device resources. And if the underlying hardware on the target is unable to keep up with the speed, the cache fills up and throttling write speeds, for example. And in flash arrays too, there is erased flash blocks for faster writing. And if the device runs low on these erased flash blocks, the cleanup process could take up the device resources, slowing down the device. So these are just a few situations, but these sort of inefficiencies in the target implementations or the host implementations can be caught using these latency timings or exchange age times. So here I'm going to talk through another debug example. This is a pretty zoomed in graph on a real SAN where the megabytes per second was intermittently dipping. So instead of showing the full capture here, we are just zooming into that portion where the megabytes per second was dipping, and it would actually go down to a 0, stalling all data. Of course, in this case, before we proceeded to looking at upper layer exchange timings, first things first, we looked at if there were any errors on the link and if there were any buffer-to-buffer credit situations or buffer-to-buffer credit loss. And after doing all that, then we came up to looking at the pending IOs at the host side. So on the left side graph is showing megabytes per second dip, and on the right side, we plotted the pending IOs from the host. And as you can see, the yellow graph there shows that the pending IOs were kept consistent from the host. So it gives us an idea that there were pending IOs on the link, but somehow the megabytes per second was still down. Then the next metric we plotted was the exchange age, which is in sort of the pink graph there. The exchange age showed that after the megabytes per second dropped, the exchange age times increased by almost 8 times on that link. So that tells us something that related to the exchange age times actually caused the megabyte per second drop. And the next thing we plotted in the blue graph there was the first response time, assuming that the target was not sending data in time. Maybe that was causing the exchange age latencies. But then when we looked at the blue graph, we figured out that the target was sending there was no difference in or increase in the first response time, which is the first command to data time on that link. So then we proceeded, to looking at the last data to status time, which is again the time it takes for the target to send the status after the last data has been sent. And that in purple, the purple graph there at the very end shows that after the performance dip, the last data to status times increased again by a scale of 8. And that tells us that all the data was sent back from the target. There was no data time delays. There were no first command to data time delay, which is the first response time, but the last data to status time was increased, and in this case, that was the reason for the dip in the megabytes per second. And in this particular case, it so happened that the back-end hardware of the back-end bus of the target between the controller and the hardware was congested, and the target wasn't able to deliver the statuses after completing the data for all the pending IOs. It wasn't delivering the statuses in time, which was showing up as a performance dip on the entire link. So, and the point we're trying to drive at is that the exchange timings in a topology can point out to topology inefficiencies. We want to look at these as the last step in debugging your performance issues. And the systematic approach, walking through the layers, walking through different layers in the protocol stack, can help ruling out lower layer issues is very important in debugging these issues, debugging these performance problems. And if we look at this situation here, the credit starvation might as well show these same symptoms. If we don't rule out the credit starvation problem first, it might look like the target is not sending frames, so it's a stalling on the target side. But because we were able to follow the transmit credit counters and able to figure out that there was no credit issues on this link, then we plotted the exchange ages and looked at those metrics to figure out that the actual issue was in a target inefficiency on the backside of its controller bus. So here we're going to, so then we talked about the host and target inefficiencies. There could also be the fabric congestion, which would be causing the delay in completing operations, IOs, and that could be looked at using the same metrics, but it depends on where we measure these metrics. So in this diagram here, you see that the red lines show the various links where these metrics could be measured. If you're measuring this metric on a host port or on a link from the host to the fabric using inline capturing mechanism or the port metrics, you will see that for example, the command to first data time would include the latency of the fabric as well as the target, right? It would include the fabric and target latencies. But the same measurement on a target link or a target port would simply give you the target latency. So when we measure these two, and depending on where the measurements are taken, we could actually figure out if the latency was being caused by the fabric instead of the host or the target port. So here I have a quick debug example to show that. The red graph there shows a throughput dip on a fiber channel link connected through from a host to a target, and there were switches in between. So we captured traffic on both sides of the fabric and measured the command to first data time on either sides of the fabric. And when we look at these average values, the command to data time or the first response time on one side of the fabric is almost double the amount on the other side of the fabric. So depending on your topology, you should be able to figure out how much latency you're expecting in these fabric when a frame passes through the fabric. And this cross-port latency sort of gives you an idea of, okay, is my host causing this issue, my target, or the fabric in between is causing this issue. So the same set of metrics we can use to detect fabric delay depending on where in the topology you're measuring these. All right, having said that, I'm going to pass it back to David for talking through jamming scenarios. David?
Thanks, Yamini. So, we're talking about all the things we can test and how we can test. One of the key implements of test is remediation validation. So, presuming you've got an analyzer and you've got the information that we've discussed thus far, and you've determined that you have a problem, and you get some solutions out of that from your vendors, how do you go about using a tool to help you validate that? And across the board, as you look back at the graphic that we showed earlier, where our tools applied at what levels, jamming in the data center becomes very valuable when you're going to be replacing componentry or even adding new components to build up to see what the effect of those things might be on your system before going live. So some of the specific errors, test fabrics can be things like emulating a cable pull. What happens if somebody kicks your cable out of the switch? Modifying or altering your advertisement of speed negotiation and your transmitter training. Altering primitives, specifically to obfuscate what the packet is supposed to be. The purpose is here to establish worst case, corner case scenarios. You'll see a repetition of these bottom 2 points on here, which is replicate customer environmental issues and optimize your error recovery algorithms. Specific to the data center managers, what you're going to want to do is you're going to want to make certain that your customers, the people that you service, are up and running all the time. So you may have a test bench where you're bringing things in, and you want to replicate those environments, and you want to beat up the tools that are used in the fabric to get to that point. So as a specific example, in jamming at the FC1 layer, to point it out, we can alter primitives, we can modify CRCs or manipulate disparity, force resets, and a variety of other things within that window, if you will, of the layers of the fiber channel. Even going so far as to change the bit values. In the FC2, we're talking about the framing protocol, creating classes of exchanges that alter the service parameters. Changing OXIDs and RXIDs, introducing an abort sequence. What happens if we abort the sequence? How do we get a response to that? How does the link replicate and get back up and running? In the case of jamming at the FC3, of course, we talked about earlier the dispatcher, the traffic cop that is the link services area, and altering a variety of these parameters could certainly have negative effects on the environment, but I want to have those negative effects. When I'm using jamming, it's to impart errors into the system forcefully so I can see how I recover. Whether that's what's causing the error or how I recover from those errors. The reason for a jammer in these instances is specifically that. And it's valuable at the data center level when somebody's bringing in new equipment and new product that you want to test before you get it into your live environment. Of course, in the application protocol, the ability to modify the submission queues for NVMe or obfuscate iSCSI reads and writes and transfers. There's a variety of things that I may want to do at the application layer that not just test the fabric, if you will, in the pipeline, but also to test the applications themselves and how do they either report information or repair themselves with when they see traffic problems below them in the fiber channel stacks. And I think that's all I have.
Correct. Thank you, David and Yamini. This is Joe Kempler again, your moderator. We only had one question that probably is due to the expertise of our presenters, and the question is, will the recording of the session be made available later? The answer to that is, of course, yes. It's at fibrechannel.org/webcasts, and you'll actually start to see that in the next couple of slides. After this webcast, if you'd please rate this event, we value your feedback and it'll just allow us to make better webcasts in the future. We will post a Q&A blog at fibrechannel.org with the answer to the questions. You can also follow us on Twitter at FCIA News for updates on future webcasts. Also, if you want to visit our library, and this is where we'll post this, we have a webcast library with different seminars such as FC Fundamentals, FC Performance, FC Interoperability, and again, they can all be viewed on demand at fibrechannel.org.webcasts. With that, our next webcast will be Will You Still Love Me When I'm at 64 GFC. It's December 11th at 10 a.m. Pacific Daylight Time, or sorry, Standard Time at the time, and you can register at Bright Talk. With that, we hope you found this webinar educational and that you're able to use it to improve your fiber channel network in your data center. Thank you again for attending, and please look to the fibrechannel.org website for additional material. Lastly, remember all of our friends in the Florida Panhandle and the surrounding areas, be generous in your donations and make it a great day. Thank you very much. Goodbye.
Thank you.
Mr. Kimpler, if we're still online, we had a quick question about the flow control webcast by Earl Apolanis and Ed Mazurik. For those of you who just saw the slide on the webcast, that's part of the library on the FCIA. You can go in, I believe that was done in July, if I remember correctly. But no, that was earlier than that, may have been May. But it's on the website, the Fibre Channel website, so you can find those things there.
We also have a couple of other questions about ISLs, but we're actually running over our time. So our expert we have these captured. Our experts will email you, and they'll also be on the Fibre Channel blog. Thank you, and make it a great day.
Thank you all.